we're going to look at the second version of the rate law. When we first kind of started talking about this, I told you there was two different versions of the rate law. What we've done so far is called differential rate law, or we just nickname it the rate law, right? The regular one. And that's when we study how the concentration affects the rate. Okay, but the integrated rate law is going to look at how the concentration changes over time. So we're going to study basically the concentration of one thing over a certain period of time. Okay, and so we're going to start with first order rate laws. Okay, so these are substances in which our rate order is just 1, right? We've got a 1 up there as our exponent. Okay, so first order integrated rate law. It follows a set equation, right? So we have the differential rate law, and this is the integrated rate law of first order, okay? So this is differential, the one we've already done. And this is the integrated rate law. It's got a different equation, okay? And so it uses this particular equation. And at the end of this little section, probably tomorrow, I'm going to give you kind of a cheat sheet of keeping these orders separate because they all have different equations. So I'm going to give you a little sheet for that. If you want to put this somewhere, I don't know, prominent, I would highlight that equation for first order, knowing that this is the equation that we're going to use when we talk about first order reactions, okay? Would you know what LN stands for? Yeah, yep, it's calculator, so natural log. Yep, natural log of the concentration of A. Okay, so that means we would just literally plug in natural log of the concentration on our calculator, right? We're going to use that thing. K is still the rate constant. And then what do you think A sub 0 means? Any idea there? It's just the initial concentration of A. So the 0 stands for the concentration of A at time 0. Okay, and that means this concentration is like almost our final concentration, or the concentration at whatever time we're looking at. Okay, so if we have time as like 10 seconds plugged in, this A would be the concentration of it at 10 seconds. This would be my starting concentration. Okay, so they'd most likely be different. Okay, does that kind of make sense how that gets plugged in? Okay, so there is our first order integrated rate law. Okay, we can see this graph, a graph of a integrated rate law that is a straight line in this negative direction is considered first order. So when we see first order reactions, we should see a slope that looks just like this. Okay, so any reaction that is first order would have a graph that looks similar to that. Okay, a straight line in the negative direction. All right, because the natural log of our concentration will decrease as time goes on. Okay, here you see they've already done the calculation for the natural log, and they have it in the negative direction. So it's getting bigger in the negative direction there. Okay, so that's important that the graph we see is negative slope in a straight line. So if it would give you just the graph and it would ask you what order is the reaction, right? We know that first order reactions have a negative straight slope. Okay. When we study first order reactions, we are able to find what's called the half-life of a reaction. The half-life is the time it takes to reach half of its initial concentration. Okay. We study half-lives a lot with, have you heard the term half-life before? It's used in like carbon dating and like fossils and things like that. How long does it take to decompose half the way, right? So the half-life is how long it will take to get to half of its initial concentration. And here is the equation for first order reactions. Okay, so first order half-life reaction is 0.693 over K. Half-life will be measured in seconds. Okay, not days or months or years, but it'll be measured in seconds. Okay. The half-life of a particular compound is not based on the concentration, right? Half-life is based on the compound itself. So we don't have to take concentration into account when we calculate half-life. Okay, but it's a common question here. How long does it take to reach the half-life? All right, let's go ahead and try one here. this says using the data, verify that the rate law is first order and calculate the value of the rate constant. Graph natural log versus time and find the slope. Okay, so this is what we're going to do. In order to verify that it is first order, we have to graph it. So we're going to go ahead and get our data table set up of natural log, and we're going to graph it. So you need a little space. Do you need some graph paper, or can you just do it on your sheet? If you want graph paper, I have it in the glass cabinet right there. Let's go ahead and start looking at our data. If we know that our graph, right, if I think about natural log graph, it needs to look like this. Natural log of some concentration versus time, and we're expecting a straight line slope, right? That's what would verify to us that it is first order reaction. So first thing I need to do is I'm just given my initial concentrations, so I need to convert them into natural log. So I'm just going to make another little data table entry here, natural log of N2O5, and I'm going to add that to this data table, so that I have this information for me to graph. Okay, so let's just go ahead and run those calculations for each of those concentrations. Do you know where your natural log button is? For me, it's a regular button. It's not a second function on this calculator. So I will just plug in ln of 0.1, and I'm going to write that out. Negative 2.303. Let's go ahead and stick with 3 decimals since that's what our original concentration. Actually, our original has 4. We can stick with 3, that's fine. So I'll just move all the way down the data table and collect all that data. So I've got all my natural log data, and so now I'm going to come down and actually graph it. Okay, and I'm just going to draw kind of a simple graph here. Okay. My natural log values are negative, so I'm going to keep my origin, right up here, and I'll draw my graph, where it's supposed to be. So -1, -2, -3, -4, -5, right? This will be my natural log of my concentration, and this will be time. So I need my time to run all the way to 400 seconds, so 100, 200, 300, 400, 500, right? My graph is not perfectly to scale, but I want to do the best I can to keep my scale consistent on both sides in terms of the spacing of those tick marks and stuff like that. If you get your scale really crazy or you're not kind of consistent with that, your graph could look curved when it's not supposed to look curved, or it could look straight when it's not supposed to. And so just be careful with that. Eventually in this chapter, I'm going to teach you how to graph this on your calculator, and so that's going to speed things up a little bit. But for now, I want us to go ahead and do it by hand. So my first data point is at t=0, right? And I'm not graphing this data, I'm graphing natural log, because I want to confirm that it is first order. So you don't necessarily have to cross that out, but at t=0, I'm at -2.3, so right about here. Okay, so we're just going to go ahead and graph each of these. At 100, I'm at about 2.6. -2.6. At 200, I'm about 0.3. I'm sorry, at about 3. At 300, I'm about 3.6. 3.7. Oh, wait, I'm off. Oh, I missed it. 50 was the next dot. That was my fault. Okay, so 50 is going to put us a little closer here. All right, there we go. At 200, I'm at -3.7. And all right, so I'm going to check. Does your graph look similar? Somewhere around there? Right? I'm going to look and see, does it seem straight? What do we think? Does it seem straight enough? It's pretty darn straight, right? If I'm connecting those dots, I'm not seeing any major curvature. Remembering that it's not to scale, I think we can verify that that's a first order reaction, right? We see a straight line in the negative direction. So I think we can confirm that that's a curved line. If we would see, if we were looking at a curve, we might see something like this, right? It would be a pretty noticeable curve, but I think ours looks fairly straight. So we can go ahead and confirm that it is first order. So we graphed our data. Now we want to calculate K. All right, we want to calculate the rate constant. And so we can do that by calculating the slope, okay, the slope of the line. So that means for our slope of our line, we could realistically pick any 2 points. For me, I prefer to just pick the first and the last. It doesn't really make a difference, but I like to pick that one because it has a 0, right? It makes my math a little easier. It takes away one part of, or one area that I could be making a mistake, but for the most part, you can choose any 2 points to calculate. So I'm gonna go ahead and find that, right? You might even highlight here that the slope of our graph gives us the K value, so we don't forget that. When we wanna find our rate constant, we can find it by simply finding the slope of the graph. Do you remember the formula for finding slope? What is it? Yep. So the slope value would be it's essentially rise over run. Have you heard that before? Okay, so rise is change in y, change in x. So if I'm going to choose these 2 data points, okay, that's basically this one and this one. Okay, so for K, my change in y is negative 5.075 minus negative 2.303 over 400 minus 0. Okay, are we comfortable with where those numbers came from? Of course, minus a negative becomes a plus. Remember, I'm not using my regular concentration data. I'm using my natural log because that's what I graphed. And so my K value comes out to be negative 0.00693. Okay, so how do we know the unit here for our K value? How do we know the unit? Okay, we're going to go back to the fact that we know it is first order. And if we had a first order rate law, it would look like this. K equals concentration of N2O5 to the first. And so our units really become molar per second, molar, right? So our unit here is just 1 over seconds, okay, for a first order rate constant. Well, first of all, tell me, do we feel pretty good about how we graphed and how we verified our K value? Did your guys' K come out to the same thing? Yes? Okay, I'm going to throw one extra question on this slide. Okay, I want you to find the concentration of N2O5 at 150 seconds. So I want the true concentration of it. Right, I want the actual concentration at 150 seconds. Look up here at our data table. Do we have a data point that's 150 seconds? No, it'd be somewhere in between right here. Agreed? So we have a range of at least our concentration is probably between 0.7 and 0.5. Would we agree? So that gives us kind of a range for our answer here. So now we've got to figure out how can I solve for that, right? I want to solve for N2O5 at 150 seconds. We'll come back up and use our integrated rate law equation. Okay, it's on that last slide. So the equation is natural log of N2O5 equals negative K T plus natural log of initial concentration, N2O5 sub 0, right? That's my equation I'm going to use there. Okay, do we agree with that? Okay. I need to work backwards just Actually, I'm going to show you a little connection here. I'm going to show you one thing, okay? This equation right here, it looks very similar to y equals mx plus b, doesn't it? Y equals mx plus b. So that means, look at my y value on my graph. Oops. My y on my graph was natural log. My slope is actually equal to negative k. My x value is my time, which is what was graphed here, and my y-intercept was my initial concentration. All of that makes sense, right? So now I want to walk back one thing here. When we needed to calculate our slope or our k value should have actually been positive because the slope is actually equal to negative k. All right, so since we calculated the slope and it came out negative, we're going to reverse that, right? Because the slope that we calculated is equal to negative k. I apologize, I forgot to put that in there the first time. All right, so let's keep working here. We want to find our final concentration here. So natural log of N2O5, right? This is really what we're searching for right there, that concentration. My negative k, I'm going to plug in negative 0.00693 because the negative's in the equation, times time, 150 seconds, because that's what our problem asks us for, plus the natural log of my initial concentration. Right, and our initial concentration was 0.1. So I can solve this whole right side of the equation at this point. Natural log of 0.1 Right, I can do that whole right side. I got to come out at negative 3.347 equals the natural log of N2O5. Tell me if your right side of your equation came out similar to that. My issue, I don't want the natural log of that concentration. I want the actual concentration. So how can I reverse the natural log? Any thoughts? Remember how to do that? I don't really need to know the math behind it, but on my calculator I'm going to use second natural log. That's it. Right? Just like if I wanted to reverse a multiplication, I would do the opposite of that, which is division. And so to get rid of our natural log, we're going to go second natural log, which comes out to be E caret negative 3.347, and that's going to be our concentration. So you can do second natural log of second answer, and that helps me not have to plug everything in so much. I get 0.035 mole per liter. Did that fit in our range? Oh, I talked about the wrong range before. Sorry, we wanted 150 seconds. You guys need to tell me when I do things wrong. Okay, 150 seconds, this fits better, would be somewhere between here. So between 0.25 and 0.5. 0.025 and 0.5. So now does that fit? Okay, sorry. All right, yes, that's better. All right, it fits between our range. I gave the wrong range the first time. I apologize. And then now we can look at 150 seconds, it's got a concentration of 0.035, just molar. I don't know why I put per liter. Molar. Okay, kind of a long problem, huh? When we see these types of problems, typically it might tell you the graph of natural log resulted in a straight line, right? That's telling you that it's first order and we're able to use this equation or whatever it might be. Today our practice is just going to be with first order, so we're pretty focused on that, but we are eventually going to learn 2 other versions of this, and then I'll give you a little cheat sheet to kind of help you know what you're looking for with each one. But right now our focus is really going to be on first order. So I think I've got one more practice problem here for you. A first order reaction is 35% complete in, 55 minutes. Trying to give myself some space here to write. What's the value of K? Okay, so let's try to figure out how we can work through this one. It's 35% complete at the end of 55 minutes. What's the value of K? If I were going to do the problem, I'm not given a lot of information. I'm given not enough information to do the half-life because it's not 50% complete. So I can't do that. I don't have a lot of other information. And so what I have to do is just keep my ratios intact. And so if I know it's 35% complete, I might pick the initial concentration of my substance, right? We'll just call this compound A. I might say my initial concentration is 1 molar. Okay, and at 55 minutes, we can just keep it in minutes for right now. At 55 minutes, we are 35% complete. So what does that mean? Essentially my final concentration of my substance will be? Oops. If 35% of it is gone, then what's left? 65%, which would mean my final concentration is 0.65 molar. Do you see how I kept that ratio intact? Right? You can choose any arbitrary numbers to go in here as long as you decay 35% of that, right? You take away 35% of it. So I just picked numbers that it was easy to take away 35% of. You could choose any numbers that you want. And so now I'm going to look at the first order integrated rate law. Natural log of 0.65 equals, let me pull out my equation again, I don't have it, negative K times time. We're going to keep this one in minutes. So that's going to change our K unit at the very end. Okay, so we're just going to keep it in minutes. So 55 minutes plus natural log of 1.0. Right. All right, so let's go ahead and do the math here. Oh, natural log of 1 is 0. I didn't know that. Okay, do you know what our units would be here? It's first order, and we're using minutes. Molar per minute, almost, except our molar gets canceled, right? If this is molar and this is molar, right? It's really just 1 over minutes. That's it. Yep. Okay, so we can do the same derivation of units here in this one too, right? We've got molar on both sides because anything in brackets is concentration. So it's just this one's just 1 over minutes, or minutes to the minus 1. All right, how do we feel about that? Kind of tricky, but makes you think, right? And then ends up coming together. So do you have, what did your next slide say, second order? Okay, perfect. We're going to stop right there.